Hi, in this video, we're going to look at the first of CloudCalc's capabilities as far as dynamic analysis is concerned. And this is going to be modal extraction. Modes of vibration are the various tendencies that a multi-degree of freedom system may have to vibrate. Each mode of vibration will have its given shape, its unique shape, as well as a natural frequency that can be calculated. So when we do a modal extraction of a piping system, you'll get to see what are the different ways that this system may vibrate, what are the various frequencies that these various modes will vibrate in. And from there, we can determine how the system may vibrate or respond to a dynamic load as a whole. Okay, how do we do this? First, we go into input and dynamic load cases. First, what we have here is simply those parameters that describe how we would like to analyze or how we'd like to extract those modes of vibration. First one we have here is how many modes of vibration would we like to calculate. And that's typically done from the lowest frequency to the highest. So if we say 5, we'll probably get the 5 lowest natural frequencies, or the modes of vibration with the 5 lowest natural frequencies. If we change that to 10, for example, we'll get the modes of vibration with the 10 lowest natural frequencies. Next, we have the option of specifying a frequency cutoff. We can say once we get to a particular frequency in hertz, which is cycles per second, then it will cut off the calculation. So traditionally, for a lot of applications, 33 hertz is considered rigid, no longer responding to much of a dynamic load. So you may optionally want to cut off your calculation at 33 hertz. If we say 0, then it means ignore this particular option here, and we'll simply calculate the 10 modes of vibration without stopping at some particular frequency or another. Normalize is we're going to get mode shapes. They're going to be generally, if we say normalize them to unity, they're going to be unitless. They're going to be scaled where the maximum displacement or the maximum vibration point in the location and direction is set to 1. If we say normalize these to mass, the mode shapes will be multiplied by the amount of mass that is allocated to that mode shape. So it's just two ways of looking at this. In reality, this probably won't affect you too much for most calculations. Static condition, we'll talk about this in a little bit more detail, but it's basically with the different static load cases that you can run, operating case, with nonlinear restraints in different situations, conditions, or with different fluid cases, different weights. Every load case may be different from not only a static point of view, but from a dynamic point of view. So this is used to pick the conditions from one of the static load cases that you want to run in the dynamic case. And we'll take a look at this implication of this in a bit. And friction factor, this again is determined if you have friction in the model, in the static model. We'll talk a little bit more about how that works. For the moment, we'll set this to 0 and move on. So we've set our parameters. We're going to take out the 10 lowest modes of vibration. We're going to ignore the frequency cutoff. We're going to normalize the modes of vibration so the maximum displacement is 1. And we're going to look at load case 1. And if we look at load case 1, or we're going to do the dynamic analysis under the conditions of static load case 1. And if we look at that static load case 1, we'll see that's with a self-weight and fluid case 1 in it. If we have a nonlinear restraints, which I don't believe we have here, we do not, then we're going to, we'd run with those conditions. So let's do the analysis. You simply say analysis, dynamic, and it goes through and it does the calculation here. This tab here shows the various frequencies. We took out our 10 modes of vibration from high to low. You get your frequencies returned in angular frequency, which is radians per second, frequency, natural frequency in hertz. 2.6 hertz is the lowest natural frequency, up to 28, and in period, which is 1 divided by the frequency. In other words, seconds between the cycles. If we want to look at what the shapes, mode shapes are, then we can see this is scaled to 1 maximum. So we see that node 160, which is here, in the x direction is going to be our maximum displacement. Everything else is scaled off of that. If we go to number 2 and take a look, this is mode 2. We see that node 229, which is over here, this elbow on the other side, is our maximum displacement in the x direction. Alternatively, we can go through and look at a text point of view, or we can go through and animate these. So you click this little icon that says animate current mode shape, and we'll see what the vibration looks like. This is the first mode of vibration. There's basically this bottom run of pipe, this bottom loop swinging back and forth. We want to look at the second mode of vibration. Click next. And we see it's the two elbows swinging back and forth relative to each other. We want to look at the third. Then it's this riser, or this run of pipe up here, swinging up and down. If we look at this graphically, we can see that it's 78, this node here, this elbow running back and forth is their maximum displacement, and so forth. And you can go through and look at each of this displacement, either from a text point of view or from a graphic point of view. Okay, now let's look at some of the things here. I went through it when we did this analysis. We chose static load case 1, which was with fluid. We got a natural frequency of 2.6 hertz as our lowest natural frequency, our fundamental frequency. If we want to go and analyze this under a different condition, for example, we may want to look at it empty. So what happens if it's empty? There's less mass. Natural frequency is basically the square root of K, stiffness over M, mass. So we should expect with an empty pipe a slightly higher natural frequency. That would be L3. We can go back to our dynamic load case and say, let's now run this in the conditions, or under the conditions of static load case 3, and see what happens if it runs empty. Or how does this vibrate it when it's empty? So we go through the analysis, and basically it's now 2.7 hertz rather than 2.6. So not that big a change, but you will see that because there's no fluid in here now, that we are going to get a slightly different, slightly higher natural frequency. And again, we can look at these different shapes. And since we don't see that big of a difference, it's not surprising that the modes of vibration, the animation, is not that much different either. However, okay, so what we can do here, again, just in review, is dynamic load cases. We can say how many modes we want to take out. We can do a frequency cutoff after a certain value. We can say I'm no longer interested. Show the mode shapes normalized, or unity to normalize to 1, or normalize to the mass allocated to that mode. Set which static condition. In this case, if you have no nonlinear restraints, it would simply be fluid, or what loadings do you have on that particular static case, etc. Let's take a look at another one now. And this is going to be slightly different. I'll open this one. And what's different here? Here we have hanger design, and we have nonlinear case. And if we look at this restraint here at 40, it's going to be it's a plus Y, which is nonlinear. It's got a gap, and it's got friction, etc. So this is a nonlinear case. Likewise, we have a spring that needs to be designed. So in that case, if we go and try to do a dynamic analysis of this, and let me go ahead. I'm going to say 5 of these, load case 3. Why is it load case 3? Because 1 and 2 are imaginary hanger cases, hanger design cases, and they're not real cases, so you can't hit them with a dynamic case. Let's go ahead and do the analysis. What's this? I got a message. It says, as this model contains spring hanger design and/or nonlinear restraints, a static analysis must be run since the last modeling change in order to linearize the dynamic model. Dynamic analysis in this case can only be done on a linear model, and we have to know things like what is the spring constant, what is the conditions of the restraints, etc. So without running a static case, I don't know that. So the first thing we need to do is run a static analysis. And let's go take a look at these load cases here. I'm going to be asking it to do a spring hanger design. And then I have a number of, we have an operating case which has fluid. We have a sustained case which has fluid. Let's add one more here. And we'll say that this one's going to be empty pipe, for example. So we'll give that a self weight and then no fluid. And we'll make that a sustained case, empty pipe. Go ahead. So now we have to run the static analysis. It'll tell us which spring is used, so we'll know what stiffness to use for the spring. It'll also tell us what is the status of the nonlinear restraints, the lift off, the gap, the one-way, etc. For each of these load cases, and also which fluid's involved. So we'll have 3 different cases. For example, let's go ahead and run this. Okay, so now we've got our static analysis. So we can look, spring hanger was chosen, so we know the stiffness is 22 newtons per millimeter. If we want to see our various nonlinear restraint status, you'll see that in case 3, operating case, the restraint is, this restraint at 44 is lifted off, is not effective in either the friction or in the Y direction. If we look at it in case 4 and 5, which are sustained cases, then yes, it is active and there is friction involved. So we have 2 different sets of restraint conditions. We also have a spring hanger that is designed. We have 2 different conditions as far as the fluid's concerned as well. So let's go into the let's go into the dynamic load cases and set these up. We'll go and say, let's look at 10 different modes of vibration. Let's change the frequency cutoff to maybe 50 hertz. Normalize these here at the unity is fine. And we're going to look at first the dynamic conditions under load case, static load case 3, which is the operating case. That means it's full of fluid 1, and it has the plus Y at node 44 is not active. So we'll go ahead and we'll run this analysis, dynamic, and we got our results. We see it only took out 8 modes of vibration because it hit the frequency cutoff. If we look at 44, we see that it's moving both freely up and down and to the side, so the friction's not coming into effect, nor is the restraint because it's not active in static load case 3. If we look at our vibration here, if we look at this in the X direction, we see that yes, here it's lifting up, going side to side and lifting up. It's totally inactive. Likewise, we know that the spring has been included, the stiffness of the spring. So if we look at our natural frequencies, the base natural frequency is 8.88. Now we can go through and change it, or let's take a look at a few other modes of vibration. Okay, there's a second mode of vibration, third mode of vibration, etc., corresponding to these different frequencies. Okay, so let's go through and make some changes in our dynamic analysis here. Dynamic load case, let's change this. We're now going to look at circumstances of it hitting under load case 5 or load case 4. Load case 4 would be with the fluid in the pipe, but with the restraint active at at 0.44. So if we save that, now we shouldn't need to run the static analysis again because no changes have been made that affect static analysis since we ran it last. So let's go through and do the dynamic analysis. And now you see the modes of vibration. The vibration here at 44, no vibration up or down because of the fact that in the static case that that restraint was active. So it was active for the dynamic case as well. So you see it's no lifting up and jumping up and down. If we look at our natural frequencies, are higher because our stiffness has tended to increase here as we now have this restraint that is taking effect. If we look at our second mode of vibration, okay, and our third mode of vibration, etc. So that's if it happens, if we're looking for the dynamic response of the piping system in static load case 4. So now if we want to look at one more, we've got 9.2 hertz. And if we go and look at dynamic load case for case 5, which would be empty pipe, the natural frequency should be a little bit higher. If we go look at the results here, it is a little bit higher from 9.2 to 11.9. And if we look at our natural frequency, again, we see that this restraint is not lifting up. If we look at our mode shapes, for example, we see that's not lifting up probably in any of these, okay, etc. Now, the one thing it is doing is it's swinging back and forth at this point. The friction is not holding it down. And we know there's friction here because we have modeled it in. And how do we take that into account as far as dynamic analysis is concerned? Well, dynamic friction cannot be easily linearized for a dynamic. There's not a direct way to linearize it as far as dynamic analysis is concerned. So here we have to use a bit of a fudge factor. And so if we look at our dynamic load cases, we see this last factor, which is friction factor. And it's a way of just saying, I want to take friction into, how much do I want to take friction into account as far as dynamics is concerned? And right now it's 0, because what this is going to do is it's going to take whatever factor we put here and multiply the static orthogonal load from the selected static case times the friction factor mu, which I believe we modeled 0.3. We'd go in and find out whatever load is on that restraint, multiply it by 0.3, and then times this whatever fudge factor we put in here. So if I pick a big number, a relatively big number, it means that friction is going to be important here. If I pick a number of 0, it means ignore friction at these restraints. If I pick something in between, it's going to say, well, it's going to be sort of in between effect. So let's consider friction here as having a big impact on my dynamic analysis. And we do the analysis. You see that the natural frequency went up significantly because we added a lot of new stiffness to this. And if we look at the results, you see there's very little lateral movement at 44 now. Let's zoom in on this location. You see it's not moving up and down or pretty much side to side. So the friction's holding it down from a dynamic point of view. And typically you may have to play around with this value a little bit in order to model to get an adequate dynamic analysis model. But anyway, those are the sorts of things that we can do here as far as modal extraction of modes of vibration in CloudCalc. Come in, you can impact how many modes of vibration you want to pull out, frequency cutoff, where you want to stop, how you want to normalize your modes, which static condition you want to load this in, run this in. And remember, if you have spring hangers or you have nonlinear events, you must do a static analysis since the last one was changed. And a friction factor that allows you to play around and study different potential dynamic responses that you can get from the system. Anyway, that's CloudCalc's modal extraction, the first of our dynamic analysis capabilities. Thank you for your attention.